Hello, welcome back to the continuation of the lecture Basics of Probability Theory. So let us look at some more theorems on probability. So given an event A and an event space B that consists of the events B0 to Bn minus 1, then the theorem says that probability of A is actually equal to the sum of the probabilities of intersection of A and Bn, where n is the index of this event in the event space. So let us look at an example of this theorem. So going back to the experiment 1 we discussed in the previous video, that is toss a coin twice and note the heads and tails. So the sample space consists of 4 possible outcomes as we seen before. So now define an event space H that consists of only I heads. Then we have 3 possible events, H0, H1 and H2, where 0, 1, 2 indicate the number of heads in the particular event. So now we define another event A that consists of only tails on the second toss. So this has 2 outcomes, either tails and tails or heads and tails. We know that from the definition of the event space H, the 3 events are as follows. That is, the first event H0 is tails and tails, and second event is heads, tails, tails, heads, and so on. So but now we can see the proof of this theorem basically from this example. Now we can easily determine the sets A intersection Bn, or in this case Hn. That is, A intersection H0 is obviously the H0 itself, and A intersection H1, that is this set and this set, it is only Ht. And so finally the intersection H2, there is nothing, so that is empty set. So the probabilities of these individual intersections are basically 1 by 4 and 1 by 4 and 0, and probability of the set A, or the probability of the event A, is basically 2 by 4, that is 1 by 2. So we can clearly see that the sum of these probabilities of intersection events or intersection sets is equal to the probability of A. So this is an example for this theorem, that probability of an event A is equal to sum of the probabilities of this event intersected with A. Now let us look at the definition of conditional probability. Conditional probability can be defined between 2 events A and B, where event A is usually a subset of B. So the conditional probability is defined as the ratio of the joint probability or the probability of B, that is the larger set B. So on the first question is obviously to find the joint probability, that is probability of A, B. In the discrete probability case, the joint probability is actually equal to the probability of the intersection between the events A and B, and this is always going to be a positive value if A intersection B is not an empty set. But if A intersection B is an empty set, that is A intersection B is equal to A and B are disjoint, then the joint probability P of AB is equal to basically 0. So from example 1 or from experiment 1, the sample space has 4 outcomes. So let us define event B, which has tails, at least one tails in the outcome. So there are 3 possible outcomes, that is heads and tails, tails and heads, tails and tails. And let's define a second event A, which has heads in the first toss. So there are 2 possible outcomes. Then A intersection B has 1 possible outcome, so its probability is equal to 1 by 4, and that is joint probability is 1 by 4. And now the probability of B is equal to 3 by 4, since B has 3 possible outcomes. So the conditional probability P of A given B is equal to the ratio of these 2 probabilities, which is going to be 1 by 3. Next, let us define an event A which is disjoint with event B, that is A is equal to heads and heads, that is it has heads in both the tosses. Now we can clearly see that A intersection B is equal to an empty set. Therefore, probability of this empty set is equal to 0. That is, the joint probability is 0 in this case. And we can also see that the conditional probability is actually equal to the conditional probability of A given B is equal to probability of A, and which is equal to 1 by 4. So let's discuss the properties of conditional probability. Basically, conditional probability has same properties as a normal probability. For example, consider 2 events A and B and assume that A is a subset of B. Then the probability of A given B is always greater than or equal to 0. And moreover, the probability of the event B given event B is obviously equal to 1. So the best way to understand this is that for conditional probability for events A and B, we treat event B as a sample space. Then we can apply all the laws that are applicable to a normal probability to this conditional probability, that is probability of A given B. So obviously from this point of view, probability of B given B is equal to 1, and probability of A given B, that is an event within B, is always less than probability of B and also non-negative. Or we can also discuss from the point of view of the definition of probability itself, that is as a frequency ratio, that is the number of outcomes in the event B, the number of outcomes in event A divided by number of outcomes in event B. So conditional probability is now a ratio of the events in A, the outcomes in A by a number of outcomes in B. And the third law is, or third axiom is, when event A has n subsets, that is A1 to AN, that is the union of all these sub-events or smaller events is equal to A, then the probability of A given B is equal to the sum of individual conditional probabilities. And the next important property or next important result is that the conditional probability is the fundamental idea behind the probability, the law of total probability. This law of total probability is very useful when we actually discuss Bayes rule, or when we want to understand the Bayes rule. So this probability of A, which is also known as evidence, is equal to the sum of the products of probability, the conditional probability of A given Bi multiplied by the probability of Bi, that is the marginal probability of Bi. Next, the example discussed for the theorem 1, that is on this slide. This example is also applicable for this law of total probability. Next, we discuss the Bayes rule. Now let us look at the Bayes rule. Bayes rule is one of the most important laws that you will understand, or that you have to understand in probability theory. Given two events A and B, the event A need not be a subset of B, and also event B need not be a subset of A, but A and B should have something in common, that is intersection of A and B should not be equal to empty set. Then in such case, given the prior probability P of B and the likelihood or conditional probability P of A given B and the evidence P of A, we can actually compute the posterior probability, that is probability of B given A, or the conditional probability of B given A. So in order to find this probability, you only need to know these three probabilities. And this kind of formula is very useful when B is not directly observable. So in this example, we will describe two events A and B where B is actually observable, but we can use this example to illustrate the Bayes rule. So let us look at the experiment 2 we discussed in our previous video, that is tossing a couple of dice and observing the two numbers. That is, we have 36 possible outcomes. So now let us define two events A and B, where A has two numbers which are both even. Then obviously there are 9 possible outcomes. So the probability of A is 9 by 36, that is 1 by 4. So we have the evidence. And then let's define B, the event B, as the two numbers, the order x, y, where x is always equal to 2 and y can be any of the 6 numbers. Then obviously there are 6 possible outcomes. So the probability of event B is 1 by 6, that is 6 by 36 equal to 1 by 6. Then the probability of A given B, that is when the event B is already happened, that is we know that x is always going to be equal to 2 and y can be any of these 6 values. Then what is the probability that it also belongs to event A? Then there are obviously there are only 3 possibilities, that is when y equal to 2, 4 and 6. So there are 3 by 6. Then the probability is, or the conditional probability is 3 by 6, which is equal to 1 by 2. Now by using all these 3 values, we can plug in directly into the formula and determine the posterior probability of event B given A, which is 1 by 3. We can also find the probability of B given A directly from the definitions. That is, given that the x and y are both even, what is the probability that x is always 2, which basically says that there are only 3 chances in which event B is also, we can observe the event B given event A. So the probability is 3 by 9, which is equal to 1 by 3. So this example basically illustrates the Bayes rule. But the real advantage of Bayes rule comes when you cannot observe the event B directly. So, but you can observe event A. Then you can actually use this likelihood probability and also some prior information on B, which is basically the knowledge of B without actually observing the event A, and also the evidence A on A. Then we can actually predict, or you can actually calculate or estimate the probability of B given A. So in those situations, Bayes rule will have a very good advantage.